Good afternoon. Welcome to the third episode of Series 1 of Lunar Lies. This is the Flat Earth Falsehoods series of videos I'm making. And the first series is on Lunar Lies, and this is episode 3. The moon is small and local. In this hangout, I'm going to be looking at the common flat Earth assertion that the moon is not far away as the globe model says it is. A lot of flat earthers, not all of them, of course, because they don't all agree on everything, but a lot of flat earthers say that the moon is relatively small. For example, maybe 32 miles or 70 miles or 100 miles in diameter. They also say that the moon is relatively close to the Earth, possibly as close as 3,000 miles, maybe much closer than that, because sometimes it appears to be in front of clouds. But none of them believe, none of their models really say that the moon is as large and as far away as the globe model says it is. So we're going to look at that flat Earth claim of a small and local moon, and we're going to see why it does not correspond to observed evidence, to observations you can make. And then we're going to look at how to corroborate, how to defend the globe claim that the moon is as far away as we say it is, and therefore that the moon is as large as we say it is. So to begin, I have this GeoGebra demonstration here. At the bottom here, on the x-axis, I have 2 points that are about 2,500 miles apart from one another. And this would represent New York and San Francisco, or Los Angeles, whichever of those two cities are about 2,500 miles apart. So they represent, on a flat Earth, New York City and San Francisco, the east and the west coast of the United States. And they're looking up at the moon, which I've decided to put at about 3,500 miles above the surface of the Earth. And the diameter of this moon is about 72 miles, okay? And I think I've chosen this distance and this size so that the angular size of the moon is about 1/2 degree. So let's verify that. Let's see if the angular size of the moon is in fact 1/2 degree. Oops. Stop it. All right, let's zoom in here. Okay, and let's get the angle between our 2 lines of sight. Does not want to be, does not want to measure that angle for me. Not really sure why. Oh, select 2 lines. There we go. Okay, so that's too big of a moon. So I need to move it a little further away, or else shrink it in size. So let's do that. Let's move it further away so that its angular size corresponds to about 1/2 degree. We're going to keep tabs on that angular size down there. Okay, so it's about 1/2 degree now. So what this shows is that if the moon is about 6,800 miles above the Earth, and this particular size of about 70 miles across, it will appear to be 1/2 degree to an observer in New York and to an observer in San Francisco. But this also reveals a problem look at the part of the moon that the observer in New York sees. The observer in New York sees this part of the moon, and the observer in San Francisco sees this part of the moon. You can see that the observer on the West Coast sees a different half of the face of the moon from the half of the face of the moon that the observer in New York sees. Now, this is exaggerated as the object gets closer to the Earth. If the moon were to be about half this size and twice as close, you would see an even more dramatic change in the face of the moon that you see from the east coast of the United States versus the face of the moon that you see from the west coast of the United States. And I have multiple examples of this now. Somebody was trying to tell me, I think his name is Quantum Eraser, he was trying to say that, hi there, Mr. Michael, and hi there, Malcolm. Quantum Eraser was trying to tell me that the moon being a certain size and a certain distance gives it an angular size, and that the moon could be any distance away so long as its size corresponds to that distance to give us the same angular size of the moon as seen from Earth, and that we can't really know that any of those sizes and distances are correct. Well, I came up with this demonstration. What I have here again is a platform that represents the flat Earth. Again, 2,500 mile span, which is about the width of the United States. So G would be the East Coast, and H would be the West Coast. And then I have 4 observers, L, K, Q, and J, and I can place them anywhere in the United States between those two ends. I also have 4 circles up in the sky that each have the same angular size to an observer on Earth. In other words, each of these 4 circles, M, N, O, and P, their size and their distance give them the same angular size to the observers on Earth. Now, this farthest away one, P, this represents the moon as the globe model would say it is. So it has it at a relatively correct distance and the relatively correct size. The other 3 represent much smaller and closer moons. So, for example, we have, again, a moon about 3,400 or so miles above the surface of the Earth, with a radius corresponding to that. A radius, it looks like, of 31/2. Okay. So it has a radius of about 15.5. So it has a diameter of about 31 miles. Okay. So let's look at this moon. Okay. Let's see how this moon differs to an observer on Earth. Okay. Let's make sure I'm dealing with the right moon here. Zoom out. Okay, yeah. So observer Q is looking at the closest of all of the moons. Okay. And we can see that when observer Q is all the way over on the west coast, the moon has an angular size of 0.4865 degrees. And as he moves, and we're assuming that the moon its current location is directly above the center of the United States. Okay. So it has an angular size of 0.4865 on one coast, and also that same angular size or so on the east coast. But we notice that the angular size increases the closer you get to the center of the United States, and then diminishes again the further away you get from the center of the United States. However, this doesn't match observed reality. The angular size of the moon is virtually identical no matter where you are on the face of the Earth. So this example, this model right here, shows that the moon can't be this small and this close. So we're going to rule out observer Q and that closest moon. So let's move L over there, K over there. Now let's go to our next moon. Our next closest moon is moon N. And for that, we're going to use observer J. Okay. Now, observer J, when he's on one coast, the angular size of the moon is 0.516795. And when he's on this coast, 516,795. Okay. And we see less of a change. We see less of a change of the angular size of the moon depending on where you are in the United States. So this is better. This further away moon is more likely to match reality. Observer K is looking at an even more distant and large moon. And we can see again that the numbers, the angular size of this moon, varies less depending on where you are in the United States. And then finally, let's go to our last observer. Observer L is looking at the moon as it is described in our current globe model. Okay, so the moon is about 238 or so thousand miles away, and the moon has a diameter of like 2,159 miles or so. And we can see that the angular size here is 0.51779, and it stays 0.51779, like to that degree, to those many decimal points. We see it stay that close, that identical, that virtually identical, no matter where you are on the United States. Okay. And you can see that while this one, okay, see here, the moon that's not the real moon, the one that's far away and big in this model, but isn't as far away and big as the moon, even this one, the decimal place is 0.51764, and in the center of the United States, 0.51780. See, that's still relatively significant, a change in the angular size. Whereas the moon that we know it is, as far away and as large as it is, the 0.51779, that doesn't change no matter where you are in the United States. And this little model of mine doesn't take into account in the globe model the curve of the Earth. Okay. Now, there's one other thing that we can get from these observations, which is how much of what part of the moon would you see from these various places on Earth in the United States? So again, let's look at the moons themselves. This var angle calculation refers to how far away from a line parallel to the surface of the Earth. So imagine the line going straight through the moon this way. How far of an angle to that line is the angle that we're seeing the moon at? So you can see an observer looking at this small, close moon. Okay? Looking at the small, close moon from one coast, the angle variance of the face of the moon that he would see when he's in the middle of the United States, okay? Like that angle variance when you're smack dab right under the moon is going to be 0. There's as much as a 19.78 degree variation. And this would mean that a person in New York would see a considerably different portion of the face of the moon from a person in San Francisco. And we can repeat this observation with the other moons, okay? Again, when you're right under the moon, there's going to be an angle variation of 0. But when you go out to the coasts, an angle variation of 3.33 degrees, okay? And we can continue these observations with the further moon. That's observer L. I want observer K. Let's give me observer K. No, go away. Observer K. There we go. So if we look at observer K now, not observer L. All right. Okay. So observer K, we can see the variance angle goes from 1.69 to 1.17. So again, even this far away and large moon, you see a variation of the face of the moon depending on where you are in the United States. And so now let's go to our final moon, what we believe to be the real moon, which is very large and very far away. Okay. Let me try to select observer L. Yeah, there we go. So observer L 0.55, 0.04. Okay. So you see the very small angular variation that he sees from one coast to the other. It's just barely half a degree. Okay. What that means, here's another model. Okay. This time I'm using two observers on opposite sides of the equator. Okay. So this is somebody perhaps at the equator and the prime meridian, and this is somebody at the equator and the anti-prime meridian, probably in the ocean somewhere. Okay. So this represents the Earth. Okay. And these two observers are on opposite sides of the Earth on the equator, and they're looking at the moon, which in this model is the appropriate distance away. And what we see is that these two observers are seeing virtually identically the same face of the moon. The angle of variation between what they're both seeing is less than 2 degrees. Okay. So what this means is that these two observers are seeing virtually the same face of the moon. And this is what we see in reality. Okay. In reality, no matter where you are on the face of the Earth, you see to about within 98 or 99%, you see the same face of the moon. This means that the moon has to be far away. Okay. So these are ways you can model how far away the moon really has to be and how big the moon really has to be for its appearance to match what we observe on Earth. And I have one other thing I'd like to show you, which is a way that you can attempt to calculate for yourself how far away the moon is. Okay? In order to do this, you're going to need a friend who can take a camera and take a picture of the moon at the same zoom level that you do, preferably, at the exact same time that you do. Okay? So for my example, I'm going to pretend that I'm down near Oklahoma City and I have a friend up in Lincoln, Nebraska. And on January 28th, 2018, at 10 p.m. local time, both of us take our cameras, zoom in to the same level on both cameras, and we take a picture of the moon. We're then going to compare our two pictures. Okay. Now, because I don't actually have these pictures, I'm going to use Stellarium. Okay. Stellarium is a program that allows you to see what the night sky looks like, or the daytime sky, from anywhere on Earth at any time. And what I've done is, using Stellarium, I've taken two photos on January 28th at 10 p.m. from both of these locations. Okay. And so those two photos are here. Okay. So this photo represents Northwest Oklahoma City, and this photo represents just outside Lincoln, Nebraska. And what I do is I take them into a photo editor and I line up the stars in the two images. The reason I'm lining up the stars is that we believe the stars to be further away from the Earth than the moon. And if they are so much further away from the Earth than the moon, then when we line up the stars in the two pictures, as I've done, we can see that the position of the moon changes slightly. In fact, you can see that the moon's position changes in such a way that it covers up some stars that are visible from one location. See how the moon covers up this star here? Okay. So once we've lined up the stars in these images, then we need to find a feature on the face of the moon that we can identify in both pictures. So I'm going to zoom in a bit on the moon. And I've actually, what I've done here is I've highlighted with a single red pixel a feature on the moon. It's a particular pixel of the moon. It was a particular color. So I marked it. And then I did the same thing in the second picture. I found the exact same location on the moon, and I put a red pixel there. Then what I did is I put a yellow pixel on both of these images where that feature appeared in the other image, okay? So this red pixel corresponds to this yellow pixel. You can see they're in exactly the same place. And this yellow pixel corresponds to this red pixel. You can see again, they're in exactly the same place. Then what I do is, using my image program, I find out how far did that feature move? What is the distance between these two pixels? And the distance between these two pixels is a box 23 pixels wide and 56 pixels tall. Actually, maybe I should have done it this way and had 1 pixel less. I'm not sure about that, but so this is measuring how far away the feature moved from one layer of this image to the other, okay? So this location here, it moves all the way down there, okay? So I have the size of this rectangle, 23 by 56, so I can use the Pythagorean equation, a squared plus b squared equals c squared. I can use that identity to determine the diagonal width, the diagonal movement of that pixel, which comes out to about 60.5 pixels. The next thing we need to do is figure out how much a pixel really represents in this image. In other words, how many pixels does it take to come up with a degree of visual space in this photo? Now, Stellarium is nice in that it tells you what your field of view is at your particular zoom level. But this is, I can't be sure I trust that. What I do know is that the moon is about half a degree in angular size. Now, on this particular date, the moon was larger than half a degree in angular size. The moon was closer to 0.55 degrees angular size. So the next thing I do in my graphic editing program is I make a circle that fits the moon. Okay? So I make a circle that fits the moon, and it has to fit the moon exactly. I want it to represent exactly the size of the moon, because then I will know how many pixels in my photo represents 0.55 degrees of visual space. And it comes out to be about 372 pixels represents 0.55 degrees of visual space. Using these pieces of information, the pixel to degree ratio for my images, and the pixel offset of that feature on the face of the moon, I can figure out how many degrees that feature has moved, okay? So in order to do that, I take the number of pixels it moved, which was 60.5, and I divide that by the number of pixels per degree. So assuming the moon is 0.55 degrees in angular size and 372 pixels is a whole degree, 0.55 degrees means that 676 pixels represents a single degree. And since my feature moved 60.5 pixels, 60.5 pixels, that 60.5 pixels divided by 676 pixels per degree gives me an angular measurement of about 0.089448924 degrees. So we're dealing with about 0.08945 degrees. Okay, so that means this feature of the moon moved about 0.08945 degrees. Now there's one more piece of information that I need in order to use that information to determine how far away the moon really is. What I need to know is the distance between the two places that I took my photo. my photos. So as it turns out, the distance between the two locations is just over 365 miles. It's 365.05 miles. Now what I'm going to do is use a simple equation. I'm just going to use a simple equation that helps me find out if I know two locations and the distance between them, and I know the angle that an object appears to move when I go from point A to point B. I should really show you an image of this. Let me sketch it out in GeoGebra really quick for you. It's way better than trying to explain it without showing you a picture. All right. Show the grid. Okay. So if I have 2 points and there is a distant point over there, okay. 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 So I know points A and B, and I know the distance between them is 365 miles. I don't know the distance from A to C or from B to C, and C is the moon in our case. But I do know the angle here. And what this means is that this is really a circle. If I have 2 points and an angle between them and a point far away there, I can create a circle out of this. I can create a circle where my far off point is the center, and my 2 points are on the circumference of the circle. Okay. So now what this means is the degree here is some percentage of 360 degrees. Okay. So what I'm going to do is I'm going to take the number of degrees that I calculated the movement of, which in this case is this value here, 0.08945. I'm going to take 360 degrees, which is the angle of the whole circle, and I'm going to divide it by the angular size that I measured. Then I'm going to multiply it by the distance between these 2 points, which in this case is 365.05 miles. And then I'm going to divide it by 2 pi. And the reason I'm doing this is because I'm trying to determine essentially the radius of a circle now. The radius of the circle in this case represents the distance from the moon to each of the 2 observers. Okay? So the radius is related to the circumference of the circle, because the circumference of the circle is 2 times pi times r. I don't know this whole circumference. I just know this portion of the circumference. I know the portion of the circumference that matches this angle out of 360 degrees. So basically what I'm doing is I'm determining this whole circumference based on the amount that I know over a degree that I know. And then using that whole circumference, I divide it by 2 pi, and that gives me the radius. And when I do that, I get a radius of 233,827 miles. So I take 360 degrees, divide it by 0.08945 degrees, I multiply it by 365 miles, and I divide by 2 pi. That gives me 233,827 miles, which comes out to 376,308 kilometers. Now, using MoonCalc, I find that the reported distance to the moon at the time of these pictures was 360,364 kilometers. So I'm off by 16,000 kilometers. But that's a relatively small amount to be off by. Given these distances, I've measured pretty accurately the distance of the moon. You can do this measurement yourself. It takes a bit of coordination. It takes a bit of hard work. It takes a bit of math. And it takes a decent photo editor. But you can do these observations and you can do these calculations and you can show that the moon really is as far away as we believe it to be. And then using the distance of the moon from the Earth and using its apparent angular size from Earth, you can estimate the size of the moon. And you can show that the moon is, in fact, more than 2,000 miles across and more than 230,000 miles away. I thank you guys for watching this hangout. I hope I've presented evidence that the moon is as far away and as big as the globe model says it is. And I hope I've shown you that the small local moons that the flat earthers are convinced we have do not exist in reality. You cannot observe them in reality. And it's just another one of their falsehoods that they propagate in their flat earthitude. So again, thank you, and I hope to see you next week.